Let's go. So I started recording, and today we will be speaking about two topics related to formal models, not about data structures, not everything else. First block, first lecture is about language and topic modeling. So what is this? How it can be used for information retrieval, and what are the theoretical ideas behind? And the second topic will be related to uh, improving a query. In general, two things will be discussed. First, it's relevance feedback. So what is this, how it is used? And second is can we expand the query? Can we make a query more powerful without the help of a human? So first with the help of a human user, second without the help. Before we start, let's remember a few things about the last topic. Oh, good morning, Akram. Do you remember just 1 to 2 words how to extract from the raw audio signal harmonic parts, the wave parts? What are the mathematical procedures which can help you to do this? Fourier transform, perfect. When you take a sine function or cosine function, you take multiple of them and you try to reconstruct the original raw signal as a composition of weighted harmonics. Any other approaches? Wavelets. Okay, the other physical idea is that signal is usually fading out. So there is usually a friction in media. So air, soil, water, they try to stop waves to propagate. So in the long distance, in the long term, in long time, waves are becoming smaller and smaller. And like the better physical intuition is the wave which is not constant, but the wave which is fading out. So if you can compose the signal of such waves, there is a chance it will be more precise in modeling. That's why, for example, you can do wavelet. It's a good idea to do wavelet decomposition for long signal. And usually when we speak about audio signal, we do Fourier transform over a short period, like 100 milliseconds or something comparable. When in this range, like this effect is not actually touching the amplitude of the wave. Okay. Do you remember anything about query by Hamming? So what is this and how to perform it? What is Hamming? It's what? Window. Window of what? Hamming is da 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 da. When I'm trying to sing the song, which I don't remember, but I'm trying to find it. So I remember just some melody, and direction of changing. So like there are multiple methods of doing this. They are all mostly, like majority of these methods, are based on coarse representation. So instead of exactly writing down the frequencies of what I'm humming, what can we do? We can try to make the relative notation. So instead of saying these particular notes, this is the same, lower, higher, same, and you can represent any composition in this way. It will definitely raise false positives, but it will allow you not to skip the song, even if you miss 1 or 2 notes, if you don't match there. And as you mentioned, yeah, there are other options when you try to work with the original signal. When you assume very important thing that you can sing in slightly different tempo and in slightly different frequency range. So that's why you try to match the signal with dynamic time wrapping, meaning that you will adjust time scale to make signals match. Okay, and the algorithm is dynamic programming algorithm, which tries to find in like a square of values the path which will maximize some cost function and or minimize cost function. And in this case, yes, this is one of the algorithms. But of course, I also mentioned Google, who like 2 years ago showed the algorithm, which is based on the idea that you can split the signal into some short blocks and represent them with embeddings. So you do some convolutional recurrent networks, and for each short period of melody, you create an embedding, and then you can search with a similar way as you do in, for example, in Shazam. But in Shazam, you search for exact match, and here you can match for embeddings of song, and these embeddings are trained to be similar for humming and original music. Okay, does anyone remember what makes our voices different? So which characteristics can be used to recognize humans?
Frequency and time.
Frequency, yeah, so frequency band and frequency spectrum. My voice is maybe higher than yours and maybe lower than yours. I don't know. We can match it. But what's time? What do you mean time? In the morning, I'm not the same as in the evening.
Maybe somebody is speaking faster, somebody is speaking.
Yeah, so the tempo, of course, and also the thing
The
called
timbre.
envelope. Yeah.
The
Ikram?
timbre.
Timbre. Yeah, timbre is actually a combination of a spectrum plus an envelope. Envelope is the like if you have the frequency representation, here are the frequencies of my voice, and here is an envelope, the curve, which shows that, for example, with the same set of frequencies, I have more low frequencies, and other human has more higher frequencies in the voice. That's how it can influence the distinguishing of humans, how the recognition. And of course, today everything is done with neural networks. So all these concepts are theoretical, but in practice, you just put everything into recurrent neural network and it solves the problem for you. Okay, who remember how to remove near duplicate images? What are the approaches? What is near duplicates and how to find them and why? Actually, why to remove them? No, not how, even why. Why do we need to remove near duplicates? Mm-hmm. So yeah, the answer is very simple. So the near duplicate images are the images which are almost exactly the same and which can slightly vary in size, maybe in cropping. And if you one is relevant for search, with a high chance others are also relevant. It means that they will be grouped together in ranking. And if you just display them in the search representation, it will be all filled with the same image. And of course, that significantly drops the quality of service for a human. This can be natural because one image is copied through multiple sources. And second thing is that actually today's search engines, they use combinations of sources. For example, Google and Yandex, they use the idea of freshness. And they have, like, for example, 3 sources which you can find easily in the search representation. This will be the source of images, like the general base. Second, it's the shopping opportunities. So the same images of the same refrigerator, but with a label of price and the market. And also the freshness, for example, the freshness when the documents appeared like 7 days or less ago, and they did not fall into the general index because index is rebuilt in some period, like in a week and 2 weeks. It means that some images which appeared on the internet in the period of from last index building until now can be not present yet. So they are searched in a different way from the different servers. And of course, they can be just copies of old images. And that means that if you search for all 3 sources, even if you remove duplicates in them, when you merge them, duplicates can appear again. And in the last stage, maybe you will want to remove them after merging. Okay. A question? Mm-hmm. Mm-hmm.
So the metrics that we have used for searching, do we need to change them because we are not taking into consideration this idea of removing duplicate reasons? So do we need to replace the metrics that we studied before with new metrics?
The question is, if we say that we remove something which is meant to be relevant by a search engine doesn't we drop the quality of the search? So it means that in terms of metrics, should be metric be different? And the answer is when we search, we use notion of distance and some models like machine learning models, which try to optimize what? Satisfaction of a human, okay? So it means that when we speak about the implementation, the exploitation of the service, then we target to satisfy users, and the way how we measure satisfaction actually doesn't care about did we remove duplicates or not. Moreover, if we say that, for example, let's imagine that like an output of 10 images, where 5 will be very relevant but the same, is it good for user? Will the user be satisfied? No. Maybe yes. pFound and NDCG, they don't actually specifically target this. But I never said that these metrics are actually used in current search. And this is an interesting thing. So I can share with you, for example, the structure of pFound, because this pFound is invented, I think, I don't know, 15 years ago, and is publicly available in research paper. But today, I remember that the name of Yandex metric is called Corsa, and there are some evolutions of this metric, and they include a lot of parameters, also with respect to some duplicates, size of the snippet, and so on. And yeah, of course, they are more advanced because their task is to be more like better explaining human perception, but no one will share this metric with you. And that because this is one of the key things in search engines. If we say that let's play the same metric for Google and Yandex, they can train the same models and they will have the same quality. Of course, they want to compete. So that's one of their competitive advantages. And of course, when search engines compare themselves in quality, Yandex says, I took my metric and I'm better than Google. Google takes their metric and say, I'm better than Yandex. And usually the difference like 0.1% point, but this is what they can use for marketing, saying that we are just better than Google. And of course, the metrics are now more advanced. But for basic tasks, these metrics which we considered, of course, they are more than enough. So for starting point. Okay, the question 5, how to find the same object on images. Do you remember anything, any approach? How to, like, if you have the object from different angles. There was a word sift somewhere from there or from there, I don't know. Someone mentioned, what is sift? Four letters, sift. Scale invariant features.
Scale invariance.
Yeah, great. Obviously, of course, anything can be done with recurrent neural networks and so on. But the original approach is that we say that if the object is rigid, if it's like solid, rigid, and if you rotate it, it will not break into parts, like, I don't know, Moscow Kremlin or Statue of Liberty, they stay for ages. If you take a photo from different angles, there will some interesting points, some features, which will be representing this. For example, on the Kremlin, there is a red star on the top. And the Statue of Liberty has a crown on the head and the flame in the hand. So these things are the things which distinguish these objects from other objects. So there are other Kremlins in Russia, but none of them has red stars on the top. So we can say this is exactly Moscow Kremlin. And we can describe them with some descriptors. That's why they call descriptors, because they describe. These are usually some numbers, vectors, which are stick to some positions in the image. And of course, the task to make these descriptors are as invariant as possible. So they should not be strongly dependent on illumination, rotation, camera properties, distance, and so on. And SIFT was one of these wonderful approaches, which actually tried to solve all these questions in one time. So even if it's called scale invariant, meaning that first thing which it targets the scale of the object, it also slightly invariant to rotation, to tilt, and to illumination. So you can use SIFT to recognize objects using the technique of bag of words, which we discussed in the language part. And the last question here, so with too many questions, why text-to-features are bad for scanning for scan text retrieval. So why like if you want to find some documents, scan document, text to features will not help you.
Because they look alike, all of them.
They are local, and it means that if you have letter A in a document,
Add noise to the
noise,
noise.
a noise.
So if we take into consideration text features, it will add noise
Mhm.
to text retrieval. I mean, if you scan a text
Mhm.
in a book, if there is a texture,
Mhm.
it will add noise to the picture.
Yeah, so scanning, of course, scan text has noise, but if you say, for example, that we use text to features, they will be like two different documents, and texture will be different. But even if we binarize the image, if we remove the noise and we say that this is black and white, we will fall into the situation when most of documents in the world are typed in Times New Roman, and they like we have E and A letters most frequent in all the languages. And that means that any document will significantly match with other documents, and just text to features will say that all the scanned documents are the same, so they will be just duplicates. Wow, let's go for the lecture. I'm just tired. So first, language modeling and then topic modeling. No significant stop. So I was reading a book on explaining the science, and one of the interesting ideas in this book was that it's always very important to understand that the auditory, like you, actually understand the general message. So when I'm trying to explain something, you can be lost in some portions. And when we speak about unexperienced popularizers, unexperienced speakers, what happens if you lose an auditory? If everyone just doesn't understand what's going on, people are trying to dig into details to make it sure that everything is clear. So instead of going back and explaining the main thesis of the block, like for example, a PhD student defending a thesis will, instead of this, try to explain the meaning of letters in the formula. And this is very common behavior when you explain something. And I decided to do the following. So for each block of the lecture, I added the major idea on the very first slide for you to be sure that if we understand this block together, that everything else is just a complementary information, which gives you additional knowledge. But the major thing is here. And the major thing about language models is that language models are models of language. They can be used to generate and actually recognize texts, but generation means that we can, for example, propose the next word. And for example, in your smartphones, you have this predictive input, which is actually the language model, which predicts the word in your language. And of course, we can use these models somehow to compare text, to say that this text is the same in style, the same in topic with the other text. And so we can recognize in terms of classification, saying that this is similar, this is not, or in terms of ranking, we can say that we have a query as we build the language model for a query and language models for texts. We can try to see which texts are actually relevant to the query. So language models are generating and they are helping to do some information retrieval tasks. So things which you need to know before we start. So what is mathematical model actually? What's the model? As we remember from previous lectures, model is just a simplification. When you have a lot of things, like the language itself is a large set of all possible sentences, we need to simplify our tool. So instead of having an infinite set, let's have something finite, which can be used for generation and recognition. So model here is just the way to build and recognize the language with a limited set of objects in our hands. Why do we need the model in general? In general, models are used for very simple thing. Of course, every time you have a task related to natural language processing or anything in the life, there are two things to do. First, you run the natural experiment. As for example, instead of running navigator application in your smartphone, you just do a ride to Kazan and you just measure time. So you sit in your car and you drive to Kazan in 1 hour, 2 minutes. Perfect. Instead of this, you can do modeling of the situation. You say, I will use the model to predict the time. And this will save me 1 hour and 2 minutes in estimation of time from Innopolis to Kazan. I don't have to go there. I just want the number. And the models are very useful in terms of predicting. Instead of running the new deadly virus in the community, you can model how this virus will spread with some models of society. There is no need to do this like a natural experiment. Unfortunately, we do, but else. Which models did we already consider? So you remember the course had some things called models, and which models were here? Of course, vector space model. So it was the model of semantics. We tried to model semantics, what we humans understand as semantics, with some vector representation and show that there is at least some correlation here. So we can use it for retrieval. Deep networks, again, some models of functions. So we can say that, let's call I don't know, BERT or GPT-3 a writer. So this is the person who writes the text. So they are like models of writers. They're not that perfect, but they try to model the person who writes in Russian or English language. Small world models, again, we consider them as models for society. The languages, regular languages, context-free, context-dependent languages for modeling syntax of the language, saying that these kind of sentences can appear, these cannot. Of course, there are some outliers, but we use it in practice. And also maybe something else, okay? Just to remind you what is a language. Language is a set, okay? We remember it. Language model serves, as I mentioned, two tasks: generating and recognition. Generating is when you try to create some content, and in this task, at least for now, language models are not that good. In particular, subtasks, as for example, predictive input. In your smartphones, in Google, in Gmail, if you use Gmail, Gmail has very good predictions in terms of like phrasal verbs. Some phrases, when there's a typical ending of the letter or typical form of, it can give you 3, 4, 5 words, just which you actually wanted to write. And prediction here can be very useful. Not writing novels or writing poems. At the moment, they're not that cool as humans. But recognition is very important. So recognizing the sentences being present in some language, that's very important. And we can say that this can be from the syntactic point of view. So you can say that the syntax is a model of the language. Syntax is the way to generate sentences without any respect to the meaning, but we just care about syntax. So syntactic way is you generate the sentence, which is correct in terms of English language, but maybe meaningless. Semantic models, they generate sentences with maybe no respect to syntax, but they try to be semantically glued, semantically consistent. And the predicate is a guard which stands between your candidate and what you call a language. And this guard says, we let this sentence into the language or we don't let. So if we speak about syntax, it does satisfy conditions of syntax or does not. If we say about semantics, yeah, it's something which sounds like from this language, or this is not a case. And the language can be of the general language itself, like English, or the language of a human, like of me. So my language is different from yours because, of course, I use my own lexics. I have my own experience in speaking and reading, and I know some words, you know, some other words we can be intersecting, but some particular features will definitely be making difference between us. As other models, of course, they are not just for guarding and generating. Of course, they are trying to answer the other questions. So people use them for answering questions about the object. So model is very good for running different experiments. Language model can try us to help to answer the questions like, are the words similar? Trying to answer questions, as for example, GPT-3 is trained to answer the questions. Do they belong to the same topic? Whatever you can ask for just two texts, you can ask it for the models of these texts. And you can propose your own tasks. Did we cover some language models before? Yes. Vector space model is not actually the language model in terms of generation and recognition. So they're not that exactly in this field. But Chomsky models, like finite state automata, context free grammars, and so on, they are actually the models of languages. They can be used for answering some questions about sentences. They can be used to recognize and generate text. Okay, so the simplest possible language model is the model which is, okay, you remember we have a set of sentences, and this set here is, for some reason, the authors of the book decided to use sigma in a sum and together to name the set. So this sigma is not the same sigma. So this is sum, and this is a language. Okay, sigma star. And this formula says the following. So we take all the sentences from the language. We use probability of seeing this sentence in the language. And these probabilities should sum up into 1, because these are probabilities. So how to use this for recognition? So if you have a sentence, you check probability of the sentence. If this is more than 0, this is the part of the language. If this is 0 exactly, so there is no chance for the sentence to be a part of the language. How to generate sentences? Just sample this distribution. If this is distribution, just with probability of the sentence, grab this sentence from the set. And this is how to generate texts in the language, the simplest possible model. The only problem here is that building such a distribution, it's a tricky thing because this set is infinite. Yeah, so where to store it? How to generate a distribution of potentially infinite set? I don't know. So no one knows. So how to do this? That's why we need to do some additional steps to create this distribution from some limited objects. So we will try to split this into parts. And how to do this? Here comes the first simplest thing ever, called the unigram model. We will meet it again later when we will generalize language models, but the unigram model says the following. Let's build the big vector. Here will be the words, and here will be the probabilities. Maybe you remember the term stochastic matrix, stochastic vector. This is the mathematical object which has the following limitation. So in a column, everything should sum up into 1, and the values of objects are values here. The numbers are from 0 to 1. So they model probabilities. And if the matrix or vector is stochastic, meaning that it should sum up into 1. So sum is 1. So this is exactly what we wanted to see. And our idea is to find such vector for our language. Here we call language some something, English language or my English language, or English language of collection of texts. So some English language. The good thing about these languages, which I mentioned, they of course based on not the understanding that there is an infinite number of sentences. It is based on exact number of examples. So Wikipedia is limited. My previous experience in speaking is limited. If you take any website, for example, scientific website, it is limited. So now for building a unigram model, you can say there is a limited vocabulary. So if you put vocabulary as the dimensions, there's always the limit of this factor. So there's 1 million of words, but we know these million of words. We just build a set of all distinct words, and we are done. Second, we can measure the approximation of probability. So how to approximate probability on a large scale? We approximate probability with frequencies. So how frequent is the word? So what's the idea of, like, for me, it's very important always to just find the difference between probability and frequency. Probability is whatever we don't know, actually. So there is some theoretical probability theory idea, distribution, which we want to learn. So we assume there is some model behind the texts, but we don't know it. And we want to approximate it with our experiments. And what is our experiment? We measure the frequency. Of course, if we measure the frequency, we can be not that precise. Maybe in future, if this writer, for example, Leo Tolstoy is dead, for example, I know who is still alive, Stephen King, he's alive. We take the previous texts of Stephen King, and we sample all the words he uses in his past. And we build the model where frequencies approximate the probabilities. And we will use them, for example, to predict the frequencies in these future texts. And we can be slightly wrong, because this is approximation. This is not exactly learned parameters. But the more text he writes, the more we exact in defining his actual probabilities. So that's what we understand. Probability is what we want to know. Frequency is how we learn this. So we know how to do this. And what unigram model says? The unigram model says that we need to find this P of S, probability of sentence, in some way. How we do this? So we say that sentences can be of different length. So we have this matrix of frequencies of words. And we add additional symbol here, the stop symbol, saying that words, stop. And we use this to find the result in the following way. So we use this part, the same probability of this sequence. But if we, for example, use this approach, what will happen? The longer is the text, the lower is probability. The shorter is text, the highest probability. If you have the frequency of letters here, so P of A, P of B, and so on, from your model, then as this is a stochastic matrix, then the text A, B, C, D up to Z, their probabilities will sum up into 1. Okay? Because if you take them, just sample them from the model. We have a stochastic vector. If you just take the sentences of one word length, they will be summed into 1. There is no place for other sentences longer than 1 symbol. So there should be some mechanism in this model which will go and grab some probability from these sentences. And this model is probability of ending the sentence. So there is some probability of stop symbol, probability of the fact that the sentence is of length 1, sentence of length 2, and so on. And we, for each time, if it's not the final term, we multiply by probability of not stopping, and in the end, multiply by probability of stopping. So how it works? So for example, we have the vocabulary of AB. So 2 symbols with probability of 1/2. So this is our vocabulary, two words, A and B. So and let's define the probability of terminating the sentence is 1/2. So what it means for us? It means that probability of text A, the same as probability of text B, is 1/2 to generate the first symbol by probability of non-stop, 1/2. And then the probability of stopping the sentence. And altogether it's 1/2 for probability of A 1/2 probability of non-stop, and then probability of stop, if I'm not mistaken. Maybe there is something.
Why the probability of stop and non-stop are both 1 divided by 2?
So because if probability of stop is 1/2, then you will proceed with the probability of one. If probability, you remember P found, there was a probability of continuum 0.85, then probability of stop is 0.15. So they should just sum up into one. You either go or no go.
Like flipping a coin.
Yeah. So maybe I'm wrong here with some numbers, but the idea is that for now the probability falls into short text is not summed into one; it's 1/4. The probability of text of length 2 is 1/8, and if you sum up these things, you will end up with 1 for all possible lengths. So if you do this, you will have 1 in a sum of all probabilities of all texts. The longer is the text, the lower is the probability, but still it's more than 0. So if we're potentially infinite, they are very small, but still not equal to 0. In practice, when we speak about modeling of the language, and we will see it in the retrieval part, the constant part, which is probabilities of stops and probability of finishing, if we fix the length of the object, for example, the query is given, okay? So we don't care about the length of the query anymore. So there will be probability of non-stop in power of n, where n is the length of this query, by probability of stop. So this part will be constant. And for computation of relevance, for example, if we use language model, it will be constant for all the computation. So it will be the part of this out of a product. And in practice, we have to consider this. But in practice, this part is omitted. So in some formulas, you'll find that the probability of query is just the multiplication of probability of term. This is not mathematically strict, but this is practice. And when we compare models, in these models, these constant factors are also constant. What are types of probabilistic models? Usually, if we generally define the language model, the model for generating language, given some probability distributions, it's very simple. You have a probability of generating the first word, and then there is some iterative process. Having this word, what is the chance to get the next word? And you sample from this distribution with this probability. Having these two words, T1, T2, what is the chance to generate the third word? So having this, if you have this distribution, you can do this, and so on, so on, so on. Of course, we have a problem for pretty long sentences. What is P of T1? If you have T1 as a term, so to store these values, you need a vector. If you have conditional probabilities T2 given T1, you have a matrix for T1 for condition, T2 for sampling. So it's a square matrix, million by million. So here, obviously, a cubic matrix. Yeah. So and so on, so on. So for modeling in general way the language, we need more and more memory. So we can try to do what? To add some constraints to our model, and to maybe reduce the influence of memory consumption. Unigram model is very simple. The next word is never affected by the previous word. This is wrong for language. You understand that language is redundant, but this is what we can use at the first glance. So we just say that we have some distribution, some words appear. Of course, text generated by such model will be something strange, but recognition can work pretty well. Okay. If we want to be more precise in generation, let's give it a Markov property. Markov property means that the next thing depends on the previous thing and not on two before. So Markov property here is for bigram model. So you have the probabilities of T1 and conditional probabilities, which is a square matrix. The question is, can we build a bigram model? So how to find P of T1? Obviously, just to approximate it with frequency of words. Okay, you take the collection of texts and you just count what's the frequency and take it as an approximation for probability. How to find conditional probabilities? Again, count. Take bigrams, 2 words in a row, and see how often these pairs appear together. The problem is that, as I mentioned, the size of this model is linear with respect to the vocabulary and quadratic with respect to this. Imagine that you need to train this model. I would say that training a unigram model is a pretty simple task, even for a small number of texts. But training a bigram model, if you have a collection of, let's say, 1,000 articles, is it enough to train a good model? So if one article has, for example, I don't know, just one page A4 is 1,800 characters, yeah? So it means that it's around, like, 300 words, okay? 300 words per one A4 paper. You have 1,000 of such pages. It's pretty big amount of text, 1,000 A4 pages. But it means that 300 by 1,000, 300,000 words. And it means that 300,000 pairs of words, like big bigrams. And you need to fill the matrix with 1 million by 1 million. So is it enough to be good in approximating this? Of course, the matrix will be sparse, especially when some things will be repeating. That means that majority of your content in the matrix will be sparse. So your model will be only very rough approximation. So that means that the more accurate is your model in terms of what you want to do, the more text you need. And this grows polynomially, not just linearly, unfortunately, with respect to number of grams here. So this is the problem of bigram model. It requires a lot of text. And also, if we go one step back to a unigram model, you remember that the formula was just including some probabilities. And that means that these probabilities are not ordered. It just cares about the count of words and doesn't care about the order of words. In this case, these two sentences in this language model will be exactly the same. Okay? The probability of them will be the same and the recognition part will be the same. Even if this can happen in Korea, I don't know, maybe in some strange cases, I believe this will never happen. So the probability of such sentences may be bigger than one, sorry, bigger than 0. And for this, I will hope to have 0 exactly. The probability of just a theoretical thing that this formula is exactly multinomial distribution. And the ideas here is that these are probabilities of terms. These are term frequencies in the sentence, which we had an example of a simple sentence. And LG is the length of the document. So altogether, they form a multinomial distribution. That's why if you have a distribution, a function distribution, we can say that this is definitely sum to 1, because this is distribution. This is the mathematically strict formula, which says that everything in this way sums up into 1. And in practice, as I mentioned, this part is usually omitted. So what we usually care about is the multiplication of probabilities. How to use language models in information retrieval. As I mentioned, we can say that the model can exist for not only the language itself, for English, Russian, or whatever, but for a language of a text, a language of a person, a language of a website. And this is the way to compare models. So you build such a probabilistic structure, and you then somehow compare them for 2 different sources of texts. And if you can compare things, then you can query and you can rank. Okay. Ranking is based on the fact that there is a procedure of seeing are these two distributions are similar. Is it possible for this query be generated by the language model of this document? And one of the most common approaches to do this is Kullback-Leibler divergence, KL divergence, which is like the default tool for comparing language models. So let's dig into details of these statements. Just to remind you, one of the terms which is actually confusing for me, term of likelihood. Likelihood, the idea of likelihood is a probability of parameters of the model observing the outcome. You understand? So you have the model which generates text. We have a text. So now let's see, is it a high chance that with this set of parameters, this text could be generated? Okay, so it's the opposite. First, we have parameters, we generate text, so it can be conditional probability. Having parameters, we have a text. This is the opposite situation. Likelihood is having the output of X, this one. What's the probability of observing these parameters in the model? Is it highly possible that it happens? Likelihood doesn't have any units. So what is stated in any definition of likelihood, you cannot use likelihood as the absolute value. Of course, as this is a probability, it scales from 0 to 1, but there's no meaning for this. So if you have two different problems, two different cases, two different models doing different tasks, the likelihood values cannot be compared in this case. What can be compared? You have the same model, you have an observation, and you can compare parameters and say, this set of parameters is more likely to be observed than this set of parameters. So they are always ad hoc, situational. Likelihood is computed and used in case we are solving the same problem, and within this small problem, we can use likelihood to compare things. And if we will try to do this, we will see that if we say that the document is getting a language for us, document is language. So here we can even, in the future in the slides, you will see MD, so MD, model of the language. So if we, how to query with likelihood. We take the text, we build the language model, MD, so the matrix of parameters, or the vector of parameters for unigram model, and we try to see how likely this set of parameters explains this query. So is it possible that this query was generated by this language? This idea is about similarity, okay? But it is defined in very different mathematical set of terms. Previously, we were speaking about cosine similarities and so on. So the vector for text, vector for query, we compare. Here we take the model for text, the model for query, and we compare models. Slightly different approach, slightly different way of comparison. What is important about this is that if we apply Bayesian rule, we will observe the following things. Probability of a document is usually what? Is usually uniform across the data set. So we have 1,000 documents, for example, or 1 billion of documents. Is there anything probable in this case? You mean what? Some documents can occur several times, but most of them usually do what? They're usually unique. So that's why in practice, probability of D is like 1 divided by n number of documents in the collection. So again, any model is a simplification. So here we say probability of having a document is uniform. So in terms of likelihood, when we compare, when we query, this is a constant factor. Probability of a query of course, it can be different. Yeah, so one queries are more frequent, other queries are less frequent, but we have this particular query. And when we do retrieval using this particular query, this part is just a denominator, which is common for any comparison. So if you compute likelihood of models of texts given a query, this given a query is constant because the query is fixed. So we are assuming this query. And that means that in practice, we do what? We just say we don't care about these two parameters. They are not removed, but they are like C multiplied by here. And what we see here, that actually the likelihood of parameters of the model is what? Is proportional to conditional probability of a query given a model. So you see they are just proportional. In simplification, in retrieval, we just say that we don't care is it D given Q or Q given D because they are proportional in our particular task. And if this is a hard task, this one is pretty like obvious how to do. We have an observation and we have the models, and we will see does this model generate these observations. As I mentioned, what is the language? Language is a pretty simple thing. It's a set of sentences. If we say that this document or this web page or this website is a language, then we model it. So we can model it with its own probabilities. And actually this procedure of preparing the bigram model or unigram model is nothing different from building a term document matrix. So you just compute frequencies of words in this language. If you have a collection of texts, and if you have a unigram model, this is exactly TDM. Yeah, so each text is a row, each term is a column, and frequencies stand in the intersection. And also the only difference is that in TDM we had different approaches to compute the values. We could use, for example, TF-IDF. We could use counts. We could use 0, 1. Here we limit our thing with like metrics should be stochastic. So what we can only put here are frequencies. Okay, number of words divided by total number of words. So to each row corresponding for each document should sum up into 1. And the relevance is computed in the following way. So we have the model, and in this model we have the probability of term. For unigram model, it's obvious how to do this. Yeah, so just take the value and you compute the probability of this phrase, of this query in this language. In some language, it can be higher. In some language, it can be lower. There is the constant factor, which we already considered from multinomial distribution and the unigram model. And as this factor is constant for a query, in terms of comparison, we don't care. Okay, so we just interested in this product. Probabilities of words multiplied by each other. What's wrong with this approach? What's the important observation which was not possible in cosine similarity approach, but definitely disturbs us here? In cosine similarity, the only chance to get 0 as metric of similarity was what? They should be orthogonal. Yeah, the query and the document should be orthogonal. In terms of vector space model based on just words without any modeling and so on, how can we do this? Simple. The words should be different. So in both texts, words should never intersect. Okay, we have like these components in one vector and other components in this. So that's why when you do dot product, you have what? You have zeros and all multiplications. If we use this model for comparison, what is dangerous? If a single word of a query is not present in the document, just a new word, this all collapses to 0. Yeah, so that's the major problem. So it means that
Can we use logarithm?
hmm? What can you use?
Logarithm.
Excuse me, the word
Log.
logarithm. So we're in the world of probability, so we'll fix it in slightly different form. So not logarithm, but something different. So then this was the question: is it actually the probability of observing a term in the model is the same as probability of generating the word by the language model? So this is a tricky thing. Is it that is it possible that this language will generate the word? The answer is maybe yes. We don't know. We just approximated the model. But in terms of our approximation in this matrix, we have 0. Yeah. So these things doesn't necessarily the same, generating the word by the model and actually probability in our approximation. They're slightly different. And how to work with this? Here comes the answer, couple of answers. So first of all, we have the language model. So previously we had the language models of documents. What if we say that there is the general vocabulary, like the language, the English, the Russian, the all words in the world? We can build such model too. And in this case, one of the approaches is to say what? If our probability of getting a term by document model is 0, or at least very small, then we will reuse the probability of the model. Okay, so we're saying that our document doesn't have the word, I don't know, hexagon, or I don't know which word, rare word, some rare word. Hexagon is a bad word. Rook. Okay, rook. So some word. Rook is a very non-frequent word. So we don't have it. So we don't have it. Just let's take the probability for this word in language in general. So let's take all the Wikipedia, parse it, and say that there is 0.000.1 probability of this word in general language. So let's substitute it. One approach, very like ad hoc approach. So we just replace one value with another in case of problem. We don't need zeros, so we will work with zeros somehow different. In this case, we just compare the probability of this word with the probability of language model. Other way is to do like linear interpolation. So we will give different weights to our model of text and the model of language, and say lambda is, let's say, 0.99. Yeah, 1 minus lambda will be 0.01. In this case, even if this one will become 0, this non-zero term and this non-zero term will sum up into non-zero value. This is at least somehow helps us to jump out of this 0 problem. And some other approaches like Bayesian smoothing, again, so term frequency divided by a length of the document is what is meant to be just a frequency. The probability of term generated by the document is this, but instead of putting 0, if this is 0, we will add some scaled factor of our general language, saying that this is still the part of English. So in case we didn't observe the word in the text, we will grab it from English and put this value adjusted to English in the model. So this one happens when you do, for example, querying. You use two models. You use two models here, and this one is about how you can do computation of model probabilities in the computational part when you collect statistics. So there's a problem of zeros. There is a way of solving this. So let's sum up models, language models. are just generally used to generate texts and recognize texts. They can be used for information retrieval. For information retrieval, we can use Unigram, Bigram, and other models. What are these models? Unigram is the simplest model, which, if we omit the scale factor, is just multiplication of probabilities of words. You can generate texts by sampling from the distribution. You can recognize texts by sampling, like by seeing the probabilities of words. The idea of retrieval is to use maximization of likelihood of a query, of the parameters of document given a query, which is proportional to the probability of query given a document. So these are exactly the same in terms of retrieval. Sometimes this approach fails when we observe words which were not present in the document. In this case, we know how to deal with zeros. And this approach is always based on the global language model. So the model of the bigger language, which with a high chance will be having the word from the query. Okay. What else? Instead of doing this, you can do something different. Instead of comparing, like running the procedure on a query, you can compare the models. And this slightly extends your opportunities in comparing. So previously it was about the query. Now you can compare any pairs of texts of non-constant length. And here comes the logarithm, as you suggested. So, and Kullback-Leibler divergence is an asymmetric divergence measure. It came from information theory, and it measures how bad the probability distribution of a query is modeling probability distribution of the document. So it's asymmetric. Of course, if you swap them, they will be not exactly the same number. So these will be different numbers. So you will need to understand what is the basis, what is the compared thing, and for example, in practice, how I use this. So I didn't use the full formula, but it's still a good idea. For example, if you want to see whether the new text found in the library actually belongs to a person. So there's a writer in 16th century, and you think that this person can be the author. You can use Kullback-Leibler divergence to check it, to test it, to see whether the distribution of this new language is comparable with the distribution of previous texts of the author. I used this part in my work, which is just examining a single word. Okay, so this is a sum for the terms of vocabulary. In my last publication, I used this part of the formula to see whether the word which I observed in the text is definitely a expected member in such a frequency in this text. So it was the statement was the following. So we have the website of texts, which is like scientifically biased. So they're all science pop texts. And I want to take one text from this collection and see which words are the most describing. And what I do, I compute for each word of this document this part of KL divergence to see whether there is a chance, the high chance of this word to be generated by the model of the whole website. If this chance is high, if the modeling is pretty good, so yes, the frequency of this word is expected to be this in this model, then this word is not distinguishing the text from others. But if the word appears significantly more frequent or significantly less frequent, we have a deviation from the model. And this part can show us in like without a scale, because it's logarithmically scaled, it helps to see is there a deviation in frequency. If there is a deviation in frequency, we can mark this word as interesting and use it for describing the text. So this is what I used for extracting what is called thesaurus, the collection of the most important words for a domain. And also, if you go for a book, you will see that it's very easy to add multilingual retrieval to such a model. If you have probability of query given a model, which is what we observe in comparison, the only thing you need to add is the matrix of translation. So in the original form, you have some words, and if you want to be able to search for queries in English for Russian texts, you just compute the matrix of translations of, let's say, Russian to English, and you add it to the model, and now you're able to compare different language texts with a simple approach. Of course, no one says this will be very good, but at least this approximation can give you some first step to solving the problem of how to make your service available for multilingual users. Okay, and for the last 10 minutes, I hope I will be able to fit. We will speak about topic modeling. The idea of topic modeling is the following. So previously, we had the language model, and we said that there is a language. Yeah, so there is something hidden, some, I don't know, spirit living in me, which make me generate the words. Okay, there is something hidden, one entity, which is a distribution of my language. Topic modeling says, no, this is not you. This is your biases. This is a set of predefined properties of me. So my interest, let's call it. I'm interested in computer science. I'm interested in playing a guitar, in playing chess, and spending time with my son. And that's why everything I talk about is not the origin of my spirit. It's the origin of topics which I'm fond of. Yeah? And that's why whatever you observe in my speech, all the words, they will be motivated by these topics. Okay, and this is about me as a human. This is about the news media. So there's a news website, and they publish some news, and they're of course different. So why the distribution of words in Meduza, for example, in Russia, and in Novaya Gazeta, and in I don't know, First Channel website will be different, because they have their own topics. One care about politics, other care about animals, others care about military news and so on. So the different topics, and that's why having these topics you generate. The interesting idea here is that I personally can be not aware of these topics, and the media cannot be aware. So they just have their own bias. So they collected the good people writing good news, and no one even asked them what you're writing about. They have their own biases, but altogether the result is some biased language model. So this is one, this is another, this is Stanislav Protasov. Like, we are all different, and the idea of topic modeling is to do what? Is to try to guess the topics given the observations. Okay, so and how to do this, we will see here. The purpose to do this, why do we actually need to observe this, is to first learn the topics. Sometimes it's very important to examine the source. Say, you are actually a political media, not the like what you claim on your website. So you say that you're posting news about kitties, but actually you write about wars and international collaborations. And second is that having these topics, what are the lexics covering this topic? What is the representative set of words which can be used to say you're speaking about politics, you're speaking about this. And how can you use these things? Of course, for example, you want to see how the topic evolves in media. So if you know that this media is using this topic, politics, which words changed for the last 50 years and how they changed, which emerged, which appeared, and this is a very interesting analysis. The major topics, as I mentioned, is one of the important questions. And actually, how many topics? It's also very important to know how many topics are there. Is it possible to learn this information? To build a topic modeling, we start with a hypothesis. Again, we limit our model. Of course, this is as any model, there is like a guess behind, and we will use this guess to build a beautiful, robust model. And the conditional dependence hypothesis says very simple things. Given a document and the topic, generation of a word depends only on the topic. Okay, so if you examine the topic in the document, the generation of word will be defined by the topic. If you have word in the topic, the document, the generation of words, the document will be defined by topics only, not by the words. Given a topic, probability of the document together with the word is defined by this generation with no additional conditions. So that they are separate. These probabilities are just independent. Probability of word, probability of topic, of document are independent if the topic is fixed. So these three things result in the following. So if we want to see the joint probability of document and word, so they appear together, then we can write in three ways, like this, or like this. So these are the same statements with respect to conditional independence hypothesis. And in the middle part, you will see that probability of document, as it will sum through the topics, can jump outside. So the document is fixed, the word is fixed. So here we can move this multiplier outside of the sum. And we get this formula. The probability of word given a document is just a combination of two probabilities, like of pairs of probabilities. Probability of the topic for a document and probability of word for a topic. And this is what the illustration of the whole process. So the document is actually defined by topics. We don't know topics, but topics influence generation of words. Okay, so we describe text as a set of topics, and that's all, nothing else. So only combination of my interests, only combination of topics of the website, and so on. And if you want to build a model of generating a word given a document, in topic modeling, we need to find these values. So we definitely can compute this. So we know what's the frequencies of words in documents. So this value is given. What we need to do, we need to find the parts of this formula. And if we look here, what is the sum of multiplications? And sum of multiplications is what? It's very, very oftenly met structure in mathematics, which is a multiplication of matrices. Yeah, so you just go through the counter and you do a dot product. So this is actually a definition of dot product, yeah, of two vectors. And if you want the matrix of all the words by all the documents, which is term document matrix, we need a matrix multiplication. And if we need this multiplication, we need the parts of this multiplication. And these parts are what? The model for topic generating words and the model of document in terms of these topics. Okay, two matrices. One is saying how topics generate words. So which words I will be using if I speak about my son. Okay, this is the topic and the words. And the second, which topics are actually my topics. So what are the parts of my internal structure or the website structure or whatever. And to do this, we do what? We do matrix decomposition. Unfortunately, this decomposition is more restricted because of very simple property. The matrix should be stochastic. If previously we were not caring about stochasticity, today we say what? So for each part of our final matrix, which is definitely stochastic, the term document matrix, the parts here also should be stochastic. So if there's a probability of generating words, probabilities should sum up to 1. If there's a probability of my topic, they should sum up into 1. So I should be fully described with probabilities, and they should be not bigger than 1. So all these values in all these two matrices, theta and phi, they are limited by 0 and 1. They are positive. They should sum up into 1. And that's why neither just SVD or just PCA will work for this task. We just cannot just split matrices into two parts. So, and having this, there should be some other methods of doing this. So how to decompose the matrix into two parts. And there are actually today two major approaches to do this. One is called PLSA, another is called LDA, latent Dirichlet allocation. This one is popularized by, I don't know about the world wide, but in Russia, the major scientist in this area is Vorontsov from MIT. And here is the link to one of the documents created by him, so in English, about topic modeling at all. So this is his topic and of his PhD students. So how can we extract topics from big collections of texts? The LDA, latent Dirichlet allocation, was invented and popularized by Blay and Andrew Ng, who is the author of the most well-known course on machine learning in Coursera. And they actually argue which model is better. And these approaches are just ways of decomposition of F into phi and theta. I think that's all. So I will not cover the details of how to do this. Actually, LDA, for example, has inside the SVD as a part, but you need to prepare the data first. And also in the GitHub, I left the link to other information material courses, which also are presented in GitHub. And also you can find, for example, the tutorials on LDA. So if you want to see how to make a topic modeling with one of the approaches, you can go there and try to do this. I would say that even if the idea is beautiful, if the model is very simple, so it's like probabilities, multiplication, interesting things. In practice, if you just try to solve the problem with this model, you will observe very strange results. So the idea behind is that if you do a matrix decomposition, what you expect to see? If this matrix is like F is words by documents, you remember what are characteristical sizes. So 1 million of documents, 1 million of words, for example. So if we decompose it into a multiplication, it will be 2 square matrices. Then to make the modeling survive, we should do what? We should find a low rank approximation, which will be of the number of topics here and of the number of topics here. So saying that we need to know this T. And in all the practical methods, unfortunately, this T is guessed by iterative process. So you cannot compute the rank easily here. But what you do, you run the run the algorithm, and then you compute the loss. The loss is usually computed with some clustering methods. So you take the silhouette score or any other approach which splits your texts into topics, and you measure the quality with this metric, and you build the curve. And this curve looks like this. So there's a loss, and it is good if you see something like this. So for a small number of clusters, this is a number of clusters, this is a loss function. For a small number of clusters, the modeling is bad. For a big number of clusters, the modeling is bad. But for some number, the split into topics is pretty good. So when the task is to find this minimum and loss, and this like the number, the rank of the matrix will be described by this value. Unfortunately, what I saw at the seminar of Vorontsov, like a year ago, maybe 2 years ago, that is this usually like this. And you need to find some other good matrices, to find the optimal topic modeling. Otherwise, if you just make a mistake in at least in one number, the topics will what? They will be interfering, and you will find in the cluster the mixture of topics. So the words which fall into the cluster will be of very different types. So I will have the word rook, the word knight, and the word sun in the same topic, even if they are from different topics in reality. So I would say that topic modeling is a hard problem. That's why it's still studied, and it's not considered as a solved problem at the moment. For this lecture, that's all. We will meet in 10 minutes. Let's say it's 10:55, and we'll continue with the next and the last topic delivered by me in this course. Okay? 10 minutes break.
Okay, thank you.
SMP is done. Yeah. You guys, I'm slowly starting the next lecture. And before we start, you remember one of the most important activities you can do in university is attendance check. Mohammed is here. Of course, Kirill. Здесь. Ayomide? Online.
Yes, I'm here.
Okay. Edelquin? Not present. Денис? Oh, класс. Хадиджа?
Here.
Okay. Роман? Нет, его Вейгу. At least his cup is here. Ikram?
Here.
Yeah. Firas?
Yes.
Елизавета? Далер? No. Ярослав? Туточки. Герман и Айдар болеют коронавирусом, да? Или что с ним, нет? Нет, живы? Okay. I heard that one of them,
Кто-то вчера был. Оба были.
they're just skipping the lecture, okay? Then that's okay. And Danil, wow, I'm so pleased to see you here. Okay, some people came. Okay, so we check the attendance, and I think we can start with the lecture. So this lecture is not that heavy because it has less formulas. It has some formulas, but they are not that counterintuitive. It groups together two topics which are not very similar in terms of how, but they're similar in terms of what for. They are similar in terms of we have a query and we want to give user a better experience. And for this, we can use either our preliminary knowledge about something, about the language, about the documents, or the knowledge obtained directly from the user, which is called relevance feedback. So today we will speak about the methods of improving the query by getting information from the user. And just a few words about the thing which you will cover in your homework and in your tutorial, in your contest. It's about suggesting continuation of queries, so adding words which are missing. Mostly the lecture is based on the chapter 9 of the book, so if you want to read it, you're welcome. And let's start with my new tradition is to introduce the major idea before explanation. So relevance feedback is the way of getting an implicit or explicit input from the user to improve the results, to obtain actually what? Obtain the information which satisfies information need of a user. The idea of relevance feedback in all the methods is to live in some vector space and to use user input to navigate in this vector space to a better location. So to either push the query into some direction or pull it, depending on what kind of feedback you get. So what kind of framework is usually considered as relevance feedback? So user runs a query, user types it in the search engine, and after user obtains some result, some relevance are with some procedure marked by user as relevant and non-relevant. And then having this new information retrieval system computes something and reruns the procedure. And it can be in multiple iterations. All the studies which are given in the book and examples with some screenshots from the slides of this book are so outdated and they look so uncommon for the 21st century that it was very hard for me to even imagine that relevance feedback still exists. But you will be surprised. First of all, 12 years ago, similar pages, like the request for a feedback from the user. So examine, you here asks the query, and instead of clicking on the document, because the document can be relevant or irrelevant, user can specifically mention that among all the search results, this one seems the most relevant for me. So I want more pages like this. Okay, and then it adjusts the results with respect to this feedback. Of course, you will not find such a link today in just Google, but you will find this in Google Scholar, and did a screenshot 2 days ago. And if you type some query in Google Scholar, for example, which is again information retrieval system, you will have at least 2 ways of giving a feedback to a system from the user. First is what? Marking this document as of your interest. This is kind of implicit feedback. That doesn't mean that this document is relevant for this query, but this document is interesting for you. You don't click it, but you mark it into some collection of your interests, which can be used later for adjusting the queries. So for example, as it usually happens, I think the example which is more or less understandable by developers, you can type the query in Google, like how to trim a string or how to reverse a string. And of course, if you don't specify the programming language, like in the raw run, you will have the mixture of different documents. But if your experience of previous searches shows that you are mostly interested in Python, then in some time, if you logged into the system, if you leave your results to the company, it will give you more and more results in your language. So it will be giving you Python documents because it is satisfying your interests more than C++ or Pascal or whatever. And of course, the related articles is exactly the type of relevance feedback. Instead of saying that, yeah, actually, I was thinking about something like this. So because why this is important? Because I was working in this area. And first of all, I mixed the term. It's a real example from my past, maybe a year and a half ago, when I was searching for hypersurface approximation. And I put some words. First of all, I've mixed hypersurface with hyperplane, which is not good. But also estimation, approximation, all the stuff was not that clear. And I was skimming through the documents and seeing no relevant to my request. I was trying to see which interpolation methods are here. But here you see some vector quantization methods of, wow, it's not what I actually meant to see. And at least one paper was satisfactory for me. And I clicked on these related articles, and it appeared that in this search, these documents were much more relevant to my initial understanding of what I was searching. And of course, the query was not just a good projection of my search. So in domain-specific search engines, you will find such situations more and more frequent. How it works? The idea of the previous algorithm, which is shown in the very beginning, how relevance feedback works, is in the pictures. These pictures are borrowed from the slides of the book. So the book has its own set of slides. The word canin, it's a Latin word for a dog, or just an aggregation of all dogs. And imagine that there is like a dimension in the vector space for canin. And if you try to retrieve some documents for this word, you will get this collection of documents. And the most relevant will be somewhere here, which uses both words with some frequency distribution. So canine is met, let's say 2 times, dog is met 3 times in this document. After this, you had some ranking of documents. And then you can say what? I want to mark this particular document as relevant now. And what will happen? In the next iteration, I will get the new run of search based on the mixed query. It will borrow information both from my initial request and from the document which I marked as relevant. And in this model, you see that these documents will be much closer than these documents, which mostly speak about cats and dogs, and mostly about cats. And here, they were on the same distance. You remember from the word canine, the distance is the same. But let me remove. So from when we started from here, distance to this document and to this document was exactly the same. After we adjusted the query to canine dog, this document and this document are much closer than this. Okay, and this is how the general idea works with illustrations. The key concept introduced in the book is the idea of centroid. I would not say that it is that important, but you just imagine that there is a set of documents, and to represent them, you need some way of doing this. And one of the most widely used way of representing a group of closely allocated vectors is what? Is finding the center of mass, so to average them. Here you see that centroid can be actually inspired by the query. So imagine you put the query somewhere, it retrieved some documents, and then you compute the centroid, which represents the results of this query. So they are not exactly the same, but they have the general nature of being attributed to these documents. The centroids can be, of course, so in this case, this centroid represents documents for a query. But if we define more subsets, for example, set of relevant documents and set of irrelevant documents, they can also be centroids for these sets. So not only for query, but for these 2 sets of documents. And the relevance feedback idea here is how to implement the algorithm, which is given in the very beginning, is to move to a vector space, first of all. And then we will move towards relevant documents, which are marked by a user as relevant, and move away from non-relevant documents. If you want to express this as a formula, we need to maximize the metric where the similarity of the new query is biggest to centroid of relevant documents, and similarity of this new query is the biggest from non-relevant documents. So we move here, so that's why it has plus, and we move from here. That's up. So if we have these 2 centroids, we just want to maximize our new query optimal, which will be a result of relevance feedback computations. This is what information hero system does after user entered the information about relevant and non-relevant documents. How to do this? Obviously, we can just say that, let's use this formula. Take the documents which are relevant, average them. So this is just sum divided by number is averaging, and minus average vector from non-relevant cluster. This is one of the initial ideas from the book. So how to do this maximization like this. So here's a small remark from me that in the book and in the slide, there is slight mixture of terms. So somewhere CR and CNR is referenced as the centroid, but here it's obviously in the formula actually the set. Okay, they're represented by this centroid. And later in the book, the set of vectors is referred as D, the set of documents. Just to make it clear that CR here is a very fuzzy term for either cluster or collection of documents. Okay, then we can find the theoretically best query, which will be somewhere here. And if we do search, it will give us the best result. So it jumps outside. It's very strange that it comes like opposite. It jumps outside of the actual region of relevant documents. But this is what the algorithm will provide us as a result. The problems with this method, of course, is the following. So first of all, user enters some relevant documents. And it doesn't mean that this set is representative. So it's like some documents. It will make our vector drift somewhere towards the user feedback. Second, this formula has nothing about original query. Okay? In this formula, we have a set of what is marked as relevant, what is marked as irrelevant, and no information about what was actually the initial query. And if the feedback is not that well balanced, as in the example in the previous picture, it's very easy to jump over and leave desired cluster of relevant documents. What we observed in the previous slide. And to work with this, a slight improvement to this original idea was added by Rocho in 1971. The idea is kind of propose a regularization technique. Instead of just blindly move the vector, we will start from the original vector and use these parameters use this shifting technique with relevant and non-relevant documents, but with some coefficients which, let's say, minimizes the effect. Not just run away, but move in the direction and see is it now better or not. What is good about this approach is that this method was practically evaluated by the author, and it has recommended parameter values. So usually when you see any model with alpha and beta as parameters, you say that, oh no, I need to tune these hyperparameters to make this model work for my problem. In their case, they did some studies and they at least have some starting points, some values which are considered by themselves as good values. So the idea is very simple. Again, very similar summations. You see the same terms. So exactly the same terms. Here comes the regularization parameters, which stops them from being 100% defining the procedure. And also it adds the original query vector always to the result. So not a significant change, but it accounts two things. First, it says we will not jump far away from the original, and we'll definitely consider the original state in the next iteration. And here are the coefficients which they propose in their study. Some comments. Of course, the higher is the number of documents we judged. So the more documents we provided in these sets, the more we want them to influence the final query. That's why maybe we need these parameters to be higher in the later iterations. So it's not that just they're constant. We want them to be more bigger and bigger with the new input. In this case, we can do what we cannot do in previous time. Even if we have a single irrelevant document, in the original model, what will happen? There will be 0 documents in the relevant set and then our query will be defined fully by irrelevant documents, which is very strange. Yeah, and this model we can even run with a single irrelevant document, which will just say, don't move in this direction, move somewhere else. And in most cases, it improves recall, but not precision. So it means that the amount of documents in the next iteration which are considered relevant will increase, but no one guarantees that this algorithm will bring you precise results. In this case, your drift will be more what I would expect to see in this algorithm. Instead of jumping over, you can drift inside the cluster of documents. What are important comments on relevance feedback procedure in general? We modify the query based on the feedback. Vector space model is our engine to do this. We use for this feedback only the documents which are marked by a user, and it can improve recall and precision. In most situations, for information retrieval, recall is more important. I spoke about this in the first lecture. You should understand that information retrieval is an experience for a human. So now we know what are information retrieval systems in practice, and we are ready to maybe skip some irrelevant documents, knowing that in the collection there are documents which of our interest. So we sometimes click on the second page of Google, or even on the third. So we use to such systems. That's why we can live with low precision, having the recall higher. What is important about relevance feedback, and which is not actually true in all the situations, is that user actually has sufficient knowledge about initial query. So as I showed in my experience, first of all, I did some mistakes and I used the wrong terminology. Yesterday, I was participating in the seminar from Elsevier, the company which is managing Scopus and ScienceDirect, the biggest editor in the world. And the person from there was showing the example of the query search for, he wanted to know like the research papers on the medicine which happens in the sea. So there are some medical treatments, medical surgeons who work on the ships. And he showed that, just imagine we have like millions of documents, millions of papers, and he searched for naval medicine. No, so he searched for marine medicine, and he found only 57 documents. Like, you just cannot imagine that there are so many scientists working in medical area, and for this pair of words, like marine medicine, he found only 57 documents. And then he used some relevance feedback from like the additional input from the user, who could observe different documents or different insights from the system. And he found out that there is also the highly correlated term, which is called naval medicine. That marine medicine was the initial query, naval medicine was the second, which give him like thousands of results. Actually, there are synonyms, but as he didn't have sufficient knowledge in the domain area, he didn't know how to call this correctly. And that's what usually happens when you search for something. You have no sufficient knowledge. And second, that the prototypes and your search is well behaved. So well behaved is, in this case, the relevant documents are similar in vector space, which is not usually true. Term distribution of non-relevant documents will be different from relevant documents, which is also not very true when you have the texts using the same words speaking about different things. This can be happening. And here are a couple of examples of violations of these assumptions. So what you need to know if you implement the relevance feedback system First, that initial knowledge can be even in misspelling. Just I don't know how to write Britney Spears' name. And cross language. Again, like the problem was that I'm thinking in Russian, and when I was translating hyperpoверхность, which is hypersurface, I for some reason just mistranslate the term into hyperspace or hyperplane. Sorry. And also the vocabulary can be different. So I came with the Russian background, and I call the person who flies into space and cosmonaut. The person who came from different background will call this person an astronaut. And this is just one of the examples. The violation of the second thing is that the distribution of relevant documents could be not exactly clustered. It can be multiple clusters. If I search for documents about pop stars worked in Burger King, from both clusters, the documents can be relevant. So I did about biographies of pop stars, and also Burger King, some publications which show information about these people. Again, multiple prototypes which are possible. So for example, the person who lives in Russia or in Eastern Ukraine will call the capital in Russian and use this kind of transliteration into English. Person who lives in Ukraine and who in Western regions who use Ukrainian language, they use a transliteration of their capital like this. And these two prototypes will even refer to the same city. They will definitely define, first of all, if you search about this city, two different clusters of terms. So because they are different in the space, but also they define very different approach to describing things, because most probably there will be very different political views of these people, and the text in these clusters will be different, and everything related to different vocabularies lead to violation of like prototypes distributed not to the compact cluster, but maybe multiple clusters in some area. What's wrong with relevance feedback as the mechanism today? So you saw that it exists, but for some reason it was removed from general web search. It still remains in some domain-specific areas. What we do, we actually expand the query. The longer is the query, the harder for search engine to deal with them. And also, this annoying procedure of not getting the document, but doing something to maybe one day find the result is not very good for lazy users. Users are lazy, they don't want to click anything to mark the documents. Original studies and the examples given in the paper were like, you see the Google page, just imagine 10 documents, and instead of clicking on the document, you first need to put ticks on these are relevant, these are irrelevant, submit. Will you ever try to do this? So like 10 documents, you need to put ticks, you need to assess them, each title. Of course, no, you just will close the search engine and change it to another. And of course, as relevance feedback is some mathematical procedure, and it works in vector space, user is not usually aware of this mechanism, and we can be very surprised by the results provided after the feedback. Okay, how to evaluate? Another problem, how to evaluate the quality of relevance feedback. So if this mechanism brings additional profit to a user, we can be able to measure it. So if there is no profit, so why should introduce this annoying technique? So to measure it, what we can do, we can first, of course, the baseline. We compute precision recall graph or any other metric for the initial query. So we say what will be if there is no relevance feedback. So we started with some query and we assess the result. After some feedback, we compute the same results And how to measure the quality. First, we assess on the same documents of the collection. It's very strange result because it's cheating. So if you give a feedback, you definitely influence the quality. So if you use relevance feedback, you will try to make it work for you. Otherwise, it's just some random shuffling. And of course, if your system is just better than Coin, then your relevance feedback will be definitely better than this, especially in case when, of course, if you mark some documents as relevant, any relevance feedback system will include them in the next search. Of course, it will not be worse than the original. So at least it is the same. And of course, evaluation should be blind. And that's why you can use residual collection of documents. So you can like hide some collection of documents from the user and do some querying and assess this hidden collection for original and for resulting queries by like other assessor, for example. And of course, this leads usually to the fact that the quality is falling, is dropping down on the second collection. But these computations are more realistic and they needed to be used for relevant comparison. So you take this residual collection and you take two queries, Q0 and QM after modification, and you compare them. But this is more valid way of comparison. Then that's it. Empirically, what is shown by the studies that usually one round of relevance feedback is enough to significantly improve the quality. Second round is marginally useful. So it usually means that you don't have to provide even the interface for the second try. Just collect the feedback from the user once. It will improve the query. And in the majority of cases, this will satisfy the user. And you cannot make it better, significantly better in your search. Of course, user is lazy. And somehow you could exclude the user from this procedure. Instead of asking user to click some buttons to mark documents as relevant, you can refer to either search results or to query user search history, to previous experience. How to do this? Obviously, pseudo relevance feedback. Assume that top K documents which you retrieved are now relevant documents. Then just drift to this set of documents, marking them as CR, the cluster of relevant documents. It works well on average, but in some cases, it can be horribly bad. And that's always the matter. So what would you like to be able to help majority of people to get slightly better results, or you want to lose some of your users because you do something awful with your results? So that's an interesting question, and you will answer by yourself when you will design a system. Of course, several iterations will drift you out of the original query somewhere where you can even not imagine you can go. The other thing is implicit feedback from user, but this feedback comes not from this particular query interaction, but with the previous example. If there is a single user, you can use previous CTR, previous experience. As I mentioned, the query of trimming a string or reversing a string. If you were previously reading the documents about C++, you can add C++ implicitly as the additional factor to your query to improve the quality and improve the relevance of documents. And of course, if there is no input from the user, what you can do, you can re-rank the documents. You can add some information based on community CTR. So if there is a community which user belongs to, either just all the users or these C++ users, see which documents around were mostly clicked by these users. And you can use these documents as relevant in this case. Instead of top K, take those which are most popular and then use them as fix for original query. So drift in their direction. So these are approaches to do the indirect feedback from user or a community of users. Great. And the last topic left. So the second lecture, even having more slides, has much less information. So I think we'll finish earlier today. The last topic is how to expand a query or suggest the finish for a query. And do it in a textual form, not in the form of vector space. What if we say that we cannot use vector space, or we would not use vector space? How can we improve our experience of a user using some other techniques? And the first idea is expansion of a query itself. In the relevance feedback, we were getting the input from the user about the documents. Yeah, so user was marking documents as relevant or irrelevant, and we made our iterations based on the input about the documents. In query expansion, user gives additional input about words or phrases appearing in the search. So I think the most obvious example looks like this. So if I do images search in Google, I type white stripes. This is a group, and there are some additions which my search engine can provide, like topics on this search. So would you like the photos of Jack White, or maybe you want White Stripes Elephant album, or maybe you want the greatest hit album picture. What else? So if you click, it will not add these words into the query, but it will like filter out and extend your query with these terms, and it will be more relevant to me. So here I click not on the document itself. I'm not given the estimation of each picture I got from the search, but I do suggest additional words to the query, which user can either accept or not accept. And of course, an original idea was just do it silently. If you do some query and query looks like very general, you can extend it with the words which are like synonyms and so on, and just do a wider search. Today, this approach is not done like this. Yes, it is implicitly done, for example, in the procedure called переколдовка in Yandex. When you take the query, of course, you try to fix the typos. You try to add very close synonyms to be more precise in search. But also, you can add things which are like improving the experience of a user. So if silent feedback gives you the chance to, with practically no quality loss, improve the result, because these are highly chance synonyms, for example. If the words mean the same, but you want, like in my case, estimation, approximation. If Google Scholar would add approximation blindly, I will find my documents faster. But it did not, so I needed to do explicit relevance feedback here. But in some cases, this cannot be just blindly done, because there is a high chance that we will affect the query. That's why you can suggest user to provide such kind of feedback. How can we augment the original query? So what are techniques to do this? So first of all, collect the manual thesaurus. Obviously, there are very close synonyms in some areas. So in Russian, doctor and врач. In English, physician, doctor, medicine, doctor, MD, medical, and so on. These words will be exact synonyms. And of course, if you search for one, you can even blindly, like just without warning the user, add these words to a query to make results more precise. I'm trying to remember what does the second line means, but I think that what it was referring to the block of the book saying that these expansion can be done by search. So instead of using a thesaurus as the hash table, for example, when you can take the query and get the match, you can do some search queries to your thesaurus, and maybe these will be not exactly synonyms, but the words which are related in some metric space to the original word. So instead of extracting this, you will, for example, also retrieve hospital, surgery, and something like this extracted by the query. So you do search for a particular term, and then you expand it with what was returned by the search results. Global analysis, again, you can derive thesaurus by co-occurrence if two words occur together as a phrase, like New York. And if you put York, you can expand the query to New York, even if it can be a mistake. But usually people search for New York rather than the York County in Great Britain. And also, you can do it based on the previous experience of other users. So there are two sources: source of documents and source of experience of users. And you don't know which is better, actually. So if you have a big source of previous information about users, query logs like click streams and so on, they are highly important source of information, even sometimes more important than just documents themselves. So and if you can see that for this query, it is usually extended with this word for majority of users, then you can add it to make this query more frequent. And also, you can do some analysis of documents in the result. For example, you retrieve some documents, and in all these documents, the query terms co-occurred together with something. So let's say I write President Lukashenko, and it gives me documents where it says President Grigory Lukashenko. And then it just extends with this word, which is frequent, and reruns the query. So it's just blindly done by the search engine in case the result set can influence the expansion. How to do thesaurus based? Automatically, so blindly, you can expand with the synonyms and highly related words. Like feline is the same for cat as canine for dog. Feline is the Latin for cat. This generally increases recall again. So you add more terms, the documents now catch the wider set of documents. So now you can search for both feline documents and cat documents. Maybe they are exclusive, not together. And this means that recall is higher, and for information retrieval systems, recall is usually more important. In science and engineering field, this can work much better than for general terms. So if you have very well defined terms, then if you have very well defined synonyms for them, it's like obviously you can use them. But it can drop precision significantly because of blurring the idea of original query. And here you can see that, for example, interest rate, which is the term in economics, it defines something exact. But if you try to extend interest with fascinate and rate as like to rate something as evaluate, then you will have something very unrelated to the original term. So it blurs the idea of original query. And of course, it's always hard to produce thesaurus manually. And whenever you do any automatic procedures, they can contain mistakes. That's what you need to consider every time you build such systems. When you generate thesaurus automatically, then you either rely on co-occurrence, and then you remember distributional hypothesis towards co-occur, then their semantics is highly close, but usually syntactical role, the part of speech, is different. And if we occur in the same grammatical situation, usually the part of speech is the same, but the semantics can be slightly different. So co-occurrence is robust, so you don't drift in semantics significantly. Grammatic relations are accurate in terms of like you will filter out the documents which will still have the original word. Quality of how the terms are associated by human or automatically is also important. Ambiguity is also a problem. In our natural languages, ambiguity appears in some very strange situations. For example, like Apple computers expanded by co-occurrence will lead to something very strange, fruitful, and red. Today's way of embedding the terms, like building the vector representation for queries, actually brings all the idea to nothing, because if the words are highly correlated, that means that they have the similar vectors. So your extension will not add something special to this search. So the technique which you should be aware of, it exists. Of course, whatever is discussed here works very good for inverted indices, which still exist, and in multiple systems they do exist. And even I can say that, for example, Elasticsearch is like a full text search, which is based on inverted indexing, not on vector space representation. That means that for such systems, all these techniques are very useful when we speak about building a product. So if you build a product which searches for something using Elasticsearch in inverted indexing, then expansion techniques are definitely good features to improve the experience of the user. But if we speak about the vector-based representations, these techniques cannot significantly improve your experience. Okay. The other thing, which is slightly different, which is very similar in terms of mechanics, but slightly different in user experience, is suggest. So you saw suggest, I think, multiple times. Like you can do it in browser, in multiple drop downs, and so on. The searcher starts typing, and the system provides some shortcuts which are trying to improve the experience. So it saves time, and it also gives some insights of what can go further. Usually this is the source of jokes about what Google is suggesting, what Yandex is suggesting, when you have some general start, like who is or how to, and very strange results come in the end. And that's why these drop downs are, first of all, managed by blacklists. If we speak about big source of information, it means that you should be able to filter out the results which contains pornography, contains violation of law, insults, blah, 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 and so on. There should be a mechanism of complaint. So there should be instruments which allow a user say that these suggest, which I found, actually insults someone and so on. Because today, being insulted is just a new norm. People sometimes see that someone saying something bad about their community, their identity, and they have the right to go into court. And if the Google says something about their identity and about their community, what should they do? They will not go into court, but there should be a mechanism for like putting the stress somewhere, and at least to Google itself, saying that please don't show me such suggests anymore. And of course, there should be some mechanics behind, and the most widely used mechanics for building a suggest is a trie data structure. In Russian, it's called also it's called the prefix tree, and in Russian it's called bor. If you search for these terms, you'll find the same structure. Bless you. And you will try a trie in your contest and in the lab. So you will try to work with trie in today and tomorrow. It's very simple and yet powerful, because when we speak about big collections of texts, it allows to compactly store big sets of texts with common prefixes, and it's highly efficient in terms of search speed. So the search speed is proportional to the length of the start, and it means that whenever you want to like see what something is in the set, it's very fast. Or whenever you want to find a subset of all the set which starts with the prefix, it returns you an iterable, like again in a very short time, in logarithmic time. Trie is naturally built for letters. That's why it works good with text. I think that this was the last part about expanding the query. Also have the example from my previous search results, showing that today suggest, of course, is not just an option to search. Today suggest is just another interface feature. And if you ever used Chrome browser, for example, you saw not only suggests to finish the word, it suggests the frequent queries, as in this third line. It suggests your previous search experience. It suggests some documents from the infrastructure. For example, in case Summer 20 is the document in my Google Drive, which I maybe reached long ago, but Google remembers that I worked with this document, and it usually suggests a couple of documents from Google Drive search in this suggest. And also, as I mentioned, previous experience of search, some URLs which contain the part of the query. So these are definitely different sources of information. So again, it can be even thought as a new search engine representation page for my subquery. So the further we go, the more complicated and the more interesting this interface part becomes. This is what I was planning to say today. Thank you for your attention. If you have any questions regarding to this topic, previous topic, today's lab, next lab, whatever contest, next lecture, you're welcome. Just to remind you that next time we have a guest lecture at 10:30. I will definitely post an like announcement, all the like introductory part, the CV of the person. This will be just a regular lecture, so please come. We will have a quiz on the lab, so at 2:30 on the 10th of March. It will be the last activity of this course, so we will not have the lesson on Thursday. So the last time we meet on Wednesday, we agree on the point. So whenever you finish the quiz, you're done. I hope Nastya will be able to grade your homeworks by the same week. So by the end of the next week, you will get the final grades. Whatever is a point for discussion, we will discuss. Otherwise, you will know your grades even before the session starts. Thank you very much for coming. see you today at the lab.
Thank you.
Bye, guys.
Thank you. Bye.